An application to Coulombs law could also be an equilibrium problem. And an equilibrium problem means that I have two particles in a field, something like a negative particle here with a charge of, we'll call it Q1, negative 6 times 10 to the negative 9th coulombs, and another negative particle over here, let's call this Q3, with a charge of negative 3 times 10 to the negative 9th coulombs. And these are a distance of 60 centimeters apart. The question is, where do I put a third particle? And it actually doesn't matter if it's positive or negative. If it's positive, it will be attracted to both sides, and if it's negative, it will be repelled by both sides. And where do I put that particle so it is in equilibrium, or it has an equal amount of force being attracted to this side or attracted to that side, or repelled by that side towards this one, or repelled to the right. So if these two charges were exactly the same, it makes sense that it would go right in the middle. We see that these charges are not exactly the same. You could maybe try to do a fraction or a ratio, but sometimes the numbers are not that easy to work with. So I'm just going to put it here and call this distance and this distance something else. I'm going to call this distance x, and I'm going to call this distance 60 minus x, and this charge Q2. So if I want to have equilibrium, I want to have the force of 1 on 2 equal to the force of 3 on 2. And when I put my formula, my Coulombs law formula in here, I have constant, charge of 1 times charge of 2 over the distance between them, which is x squared. Then constant, charge of 3 times charge of 2 over distance between them, which is 60 minus x squared. So now if I solve for x, I know the distance away from Q1 that I have to put charge particle 2 in order to be in equilibrium. So mathematically, I just can reduce out my constant. That's the same on both sides. I can also reduce out charge 2, which is what I said before. It doesn't matter what my charge is because mathematically it's going to reduce out. Q1 is negative 6 times 10 to the negative 9th over x squared. Q3 is negative 3 times 10 to the negative 9th over 60 minus x squared. I'm going to cross multiply. And when I cross multiply, I'll get negative 3 times 10 to the negative 9th x squared. I will get negative 6 times 10 to the negative 9th times 60 minus x times 60 minus x. When I just FOIL these two, I get 3,600, 60 times 60, minus 120x, and then times positive x, or no, plus x squared. That's going to be multiplied by negative 6 times 10 to the negative 9th. Still working with this side. When I then distribute this, I'm going to get negative 2.16 times 10 to the negative 5th plus 7.2 times 10 to the negative 7th x minus 6 times 10 to the negative 9th x squared. And then I'm going to put my x squared factors together. So I'm going to add 3 times 10 to the negative 9th, which will leave 0 on this side. All of this will be the same. And then if I add 3 to this, I'm going to get negative 3 times 10 to the negative 9th x squared. As you can see, this is going to set up well for the quadratic formula, which x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. You might also be able to put it in your calculator if you have a poly root finder function. When you solve for x, though, you will get 35.14 centimeters, which 2 sig figs, 35 centimeters from the first particle. A lot of mathematics there, but concept pretty basic, that the force pushing it one direction must be equal to the force pushing it the other direction.